Hi, welcome to Physics Laboratory. In this module, we are going to learn about magnetic induction. Here's the outline of our physics practicum, consisted of objectives, theory, tools and equipment, practicum procedures, and data processing. However, in this video, we are only going to cover the first three of them. First outline, objectives. This module has 5 objectives to be attained by the end of the practicum. First, to understand the concept of artificial magnet with direct current source or DC and alternative current source or AC. Second, to understand the effect of coil's number of turns and the current source towards the magnetic field. Third, to understand the induced current caused by the change of magnetic field strength and direction around the coils. Fourth, to understand the concept of simple generator. Fifth, to understand the concept of wireless energy transfer. Moving on to second outline, theory. Magnetism is a physical phenomenon explained by Ørsted that an electric current flowing in a conductor wire can yield a magnetic field effect. As you can see from the picture, the vertical line represents the wire, and right next to the wire is a compass. When an electric current is flowing through the wire, the compass needle moves as the effect of magnetic field produced from the wire. Biot-Savart then exemplified the concept in mathematics formula about the relation between electric current, the observation point, and magnetic field. It is important to note that a constant magnetic field cannot produce any current, but a change of the magnetic flux can produce electric current. According to Faraday's law of induction, the electric current is called induction current. The induction direction explained by Frederick Lenz, as in Lenz's law, is that both EMF and induction current have such direction that work against the charge producing EMF and induction current. Last but not least, tools and equipment. 1. Power supply consisted of direct current DC and alternating current AC. 2. Copper wire. 3. Iron rod. 4. Clip. 5. Solenoids with 800 turns. 6. Solenoids with 1000 turns. 7. Magnet. 8. Galvanometer. 9. Transformator. 10. Small AC generator. 11. Jumper or cable. 12. Ruler. That's the end of our video. Thank you for your attention. Have a nice day.
Assalamualaikum warahmatullahi wabarakatuh and good afternoon. Today we will practice about magnetic induction. This module is divided into 3 sections. The first is conversion from electric current into magnetic field, and the second is conversion from magnetic field into electric current, and the last is wireless power transfer. Now we will start from the first sub-module. There is some tools we need to use. The first is power supply. This power supply is different from the other power supply that used in the other module. In this power supply, there's 2 output voltage. It's AC and DC. Next is solenoid. This is the solenoid. There is 20 and 10 turn solenoid. The next tools is iron rod. The next is we will use ruler, and this is a paper clip. Then we will need jumpers. And then the last, we will need solenoid. It's 1,000 turn solenoid. Now let us start the first practicum. In this practicum, the goal is convert the electricity into a magnetic field. In this practicum, we will try to find the magnetic field strength that is needed to pull a clip. Okay, we will use the power supply. First, we will use the DC output. Okay, the next is we will connecting the coil into the DC output by using jumper. For the first, we use the 10th turn coil. Connect the power supply in the DC output to the coil by using jumper. For the first, we will use the 10 turns coil. And then put the ruler like this, and put the clips like this. Then turn on the power supply. The power supply will give electricity to the coil, and the coil will produce magnetic field. Now we will try to find the maximum distance that the clip can be pulled by the coil. Okay, let us try to put the clips 1 centimeter from the solenoid. The power supply voltage is set in 4 volts. Okay, let us try to push the reset button and see is the clip attracted by the solenoid or not. The result is the clip is attracted by the solenoid. It means the first data is 1 centimeter. Next, we try to put the clips 2 centimeter from the solenoid. Oh, and then the result is the clip attracted. Now, try to put the clips 3 centimeters from the solenoid. The result is the clip is not attracted by the solenoid. Let us try in 2.5 centimeter. Oh, the clip is attracted a little. The clip is moving, so we can say that the clip is attracted. Next, you will need to fill the first practicum observation table in the module. Number of coil you can fill with 10. The maximum distance to drag the clips you fill 1 centimeter, 2 centimeter, and 2.5 centimeter according to the experiment earlier. Then the next we'll try to use the 20 turns coil and then repeat like the previous practicum. First, we try to put the clips 2 centimeter from the solenoid. Push the reset button and the result is the clips is pulled by the solenoid. Next, let us try to put the clips 3 centimeter from the solenoid. Push the reset and the result is the clip is attracted. Let us try to put the clips 4 centimeters from the solenoid. The clips is not attracted. Try 3.5 centimeter and the clips is attracted. Now, please fill in the table according to the result of this practicum. Okay, now we will try to do the second practicum in this module. The tool that we need is a power supply, jumpers, iron rods, and the solenoid. The solenoid that we use in this practicum is the solenoid that has 1,000 turns. Now we will try to find the difference between the magnetic field that produced by the AC current and DC current. For the first, we will use the DC output from the power supply and 4 volts voltage. Then put the clips close to the iron rods. Then, then try to feel if any vibration occur in the clip. In DC current, there is no vibration. I cannot feel any vibration in the clip, but there is magnetic force that pull the clip. As you can see, the clip is pulled by the iron rods. That means there is a force that pull the clips into the iron rods. Next, try to set the voltage in 6 volts. The clip is pulled and there's a little vibration that I can feel. Next, I will set the power supply in 8 volts. The vibrations feel stronger and the force is very strong. Okay, that is for the DC current. For the 4 volts, there is no vibration, but there is a weak force that can pull the clips into the iron rods. In 6 volt, there's a little vibration and the force goes stronger. In 8 volt, the vibration feels stronger and of course the force feels stronger too. Next, let us try to use the AC output. First try in 4 volts. In AC current, I can feel a strong vibration. The vibration is very strong, but the magnetic force is not as strong as the DC. Let us try to 6 volt. The vibration feels stronger and the force feels stronger too, but not as strong as DC. Okay, let us move to 8 volts. Oh, the vibration feels very strong. It's extremely strong. The force is strong, but not as strong as DC. So, for the alternating current, in 4 volts, I can feel a strong vibration, but weak magnetic force. For the 6 and 8 volts, the vibration feels stronger and magnetic force feels stronger too, but not as strong as DC. Okay, we have done this first submodule. The goals for this first submodule is to understand about the effect of the coil amount and the current source towards the magnetic field. Next, we will do the second submodule. The tools that we need is solenoid, a simple generator, magnet, and a galvanometer. In this submodule, we will prove the Lenz's law, and EMF. Here I have a magnet. I will put it inside the solenoid. So, how we can know that there is a EMF? We can see through the galvanometer. Okay, let us try. I think this magnet is too small, so I will use the U magnet and I will put the North Pole first into the solenoid. Here, we will prove the correctness of the right-hand rule from the lens. A magnetic field is go out from the North Pole and entering to the South Pole in the magnet. Okay, I will put the magnet into the solenoid. You see the galvanometer. As you can see, when I put the North Pole first, the galvanometer will pointing to the positive, and when I pull the magnet, the galvanometer will pointing to the negative side. Then, let us try to put the south first. Galvanometer is pointing to the negative side. Now, I will pull the magnet out, and the galvanometer is pointing to the positive side. Now, let us repeat this step with slow and fast movement. Is there any difference of the deviation of the galvanometer? Can you see the differences? When I move the magnet faster, the deviation is getting further, and vice versa. And then I will try to move the magnet inside the coil and outside the coil. And you can see what's happening. When I move the magnet outside the coil, there is a current, but it is very small. Okay, next is the second practicum in the second submodule. Here, we will try to produce electricity by using a small generator. First, we will try to produce the DC current. Let us pay attention to the LED. In DC, there is only one lamp that will be turned on. Now let us try to use the AC. As you can see, both of the LED will turn on alternately. Now I will try to turn the pedal slower and faster. As you can see, when I turn the pedal faster, the LED will shine brighter. It is because when I turn the pedal faster, the magnet and the coil will produce a large EMF. In this submodule, we try to convert from the magnetic field into the electricity. Here we know EMF. There are two things that we need to analyze. The first is the effect of time on EMF, And the second is the working principle of the generator. And then the next is the third submodule, the last. It is wireless power transfer. Here we will use a transformator. It is the tools that will convert from electricity to magnetic field and from magnetic field to electricity again. And the electricity will signal to the LED. Here there is 5, 10, 15, and times 10. This is the primary coil and this is a second coil. The 5, 10, and 15 times 10 is showing the secondary coil size. When I put it in 5 times 10, it means the second coil size is 50. Here we will need the distance data, the maximum distance between the first and the secondary coil for lights to come on. Let us turn it on and try 50 for the secondary coil. Okay, let us measure the distance. It is 8 millimeter. Next, we will use 100. It is 1.3 centimeter. And last, we will try 150 turns for the second coil. And the minimum distance is 1.7 centimeter. Then we will try 200 and the distance is 2.2 centimeter. It is quite easy to analyze. The first thing is the effect of the distance on the power generated. And the second thing is what is the working principle of the transformator. That's all for this practicum. Thank you for your attention. Wassalamualaikum warahmatullahi wabarakatuh.